Imagine looking up at a star tonight, and the simple act of your eyes registering that light actually changes the path that light took billions of years ago. You are not just watching the universe. You are literally creating its past. It sounds like pure science fiction, doesn't it? Or perhaps something pulled from a late-night philosophical dorm room debate. But that idea, that totally mind-bending, counterintuitive paradox, actually comes from one of the most grounded, consequential physicists of the 20th century. A man who dealt in the hard, unforgiving math of nuclear weapons and black holes. Today, drawing from a massive stack of sources including biographies, declassified physics papers, and historical archives, we are mapping the life and the honestly, utterly unique mind of John Archibald Wheeler. If you find yourself captivated by the hidden tragedies and the profound, agonizing history behind the world's greatest minds, please take a moment to like this video, share it with a fellow thinker, and subscribe to Legendary Lives Unveiled. Your support helps us uncover the darkest mysteries of the cosmos. Consider this a fair warning. This is far from a standard, dry biography of a scientist making calculations on a chalkboard. Wheeler's life is a dramatic, sometimes deeply tragic narrative. He was a man whose career spanned the creation of the atomic bomb, the deepest, weirdest corners of quantum philosophy, and the literal naming of the universe's darkest mysteries. He categorized his intellectual life into three distinct phases. Phase 1 is everything is particles. Phase 2 is everything is fields. And his final, incredibly controversial phase, everything is information. To understand his later reality-bending theories about time and the malleability of the past, we must first dissect his fiercely debated idea that human consciousness brings the universe into existence. But because his personal life and his theoretical physics are hopelessly intertwined, we cannot grasp his science without understanding the profound, agonizing grief and the life or death pressures he experienced during the Second World War and the early days of the Cold War. Let us go all the way back to the origins of this incredibly complex mind. John Archibald Wheeler was born in 1911 in Jacksonville, Florida. His environment was steeped in data. Both of his parents were librarians, and his father, Joseph Lewis Wheeler, was a prominent library director. You would think a kid growing up surrounded by books would be quiet and constantly buried in literature. But he wasn't interested in literature for the sake of poetry or narrative. He was completely obsessed with how things worked mechanically. He would scour books with titles like Mechanisms and Mechanical Movements, and then take those schematics and physically build them. He built complex combination locks entirely out of wood. He built a repeating pistol, and he strung working telegraph wires between his house and his neighbors' houses. He had a relentless, hands-on curiosity to take the world apart and put it back together. But that level of unbridled curiosity often flirts with danger. When he was just 10 years old, his fascination with mechanisms and chemistry led him to play with dynamite caps. These were blasting caps he had found and had been explicitly warned were off limits and incredibly dangerous. He was investigating the inner workings of one of the caps when it detonated directly in his hand. The explosion completely mangled his right thumb and forefinger, and he lost portions of those digits permanently. It is a gruesome, shocking moment, but it is also darkly poetic. A kid physically blows off part of his own hand out of sheer, unadulterated curiosity about how an explosion works. And just a few decades later, this exact same person ends up handing humanity the mathematical blueprints for the ultimate explosion, the atomic bomb. His childhood explosions were a grim rehearsal for the theoretical explosions he would unleash on the entire world. Despite the physical trauma, his mind raced far ahead of his peers. He graduated high school at 15, won a scholarship to Johns Hopkins University at 16, and by the time he was 21 years old, he had already earned his PhD in physics. At 21, while most are fumbling through early adulthood, Wheeler was defending a doctoral thesis on the dispersion and absorption of helium. The physics community recognized his undeniable brilliance immediately. He secured a highly coveted National Research Council fellowship and used it to travel to Copenhagen, Denmark, specifically to work under Niels Bohr. Bohr was already a towering figure, effectively the father of quantum mechanics. In his fellowship application, Wheeler wrote that he had to work with Bohr because he sees further than any man alive. This collaboration would literally alter the course of human history. Let's jump to 1939. Wheeler is now 28 years old, working as a professor at Princeton University. Niels Bohr comes across the Atlantic bringing absolutely terrifying news from Europe. German scientists, specifically Otto Hahn and Fritz Strassmann, had successfully split the uranium atom. Nuclear fission was a confirmed reality, and the world was teetering on the absolute brink of the Second World War. The Germans had empirical evidence that fission happens, but nobody in the world fully understood how, why, or how to predict it. Bohr and Wheeler sat down in Princeton to figure out the mechanics. In September 1939, the very same month Hitler invaded Poland, they published a landmark paper introducing the liquid drop model of the atomic nucleus. This was the fundamental math that makes a nuclear weapon possible. Classical physics assumed atoms inside a piece of uranium were like solid billiard balls. Bohr and Wheeler argued that you have to completely discard that mental model. Picture the nucleus, packed with protons and neutrons, as a vibrating, jiggling droplet of ultra-dense liquid. Within that droplet, a massive, invisible tug-of-war is happening between two fundamental forces. On one side, the strong nuclear force acts very much like surface tension, pulling protons and neutrons together into a perfectly stable, tight sphere. But opposing it is electromagnetism. All protons carry a positive electrical charge, and they violently repel each other. While the surface tension holds the sphere together, the positively charged protons inside are furiously trying to push each other away, trying to rip the sphere apart. The nucleus of a heavy element like uranium is a microscopic war zone, barely holding itself together in a state of delicate equilibrium. Wheeler and Bohr modeled what happens when a single, stray, uncharged neutron is shot into that vibrating droplet. The nucleus absorbs it, adding a burst of energy, and the droplet begins to vibrate and slosh much more violently. The strong nuclear force can't maintain the perfect sphere. The droplet stretches out into an oval and then further into a dumbbell or a peanut shape. Protons gather at opposite ends of the peanut. Because the strong nuclear force only works at incredibly short distances, the protons are suddenly too far apart for the surface tension to hold them. The strong force weakens, but the electrical repulsion operates over longer distances. The electrical repulsion violently takes over, completely overwhelming the surface tension. The neck of the peanut snaps, and the single nucleus violently tears itself into two separate smaller droplets. Positively charged, they repel each other away at a significant fraction of the speed of light, releasing immense kinetic energy and spare neutrons. That is nuclear fission. Wheeler mathematically quantified the exact threshold of that surface tension. By calculating the exact balance of forces in that liquid drop, he predicted which specific isotopes would be most unstable, perched right on the very edge of snapping. He and Bohr mathematically proved that uranium-235 is highly fissile. Even more consequentially, Wheeler's math pointed to an element that didn't even exist yet in nature, plutonium-239. His calculations showed an isotope with 94 protons and 145 neutrons would be even more perfect for a chain reaction. At 28 years old, Wheeler literally wrote the instruction manual for the ingredients humanity would need to build an atomic weapon. But a theoretical breakthrough regarding unprecedented energy wasn't going to remain in a quiet Princeton classroom. History intervened brutally. World War II thrust him out of academia and into a massive industrial race. After Pearl Harbor, the government initiated the Manhattan Project, and Wheeler was recruited immediately. He started at the Metallurgical Laboratory, the Met Lab, at the University of Chicago, alongside titans like Enrico Fermi and Eugene Wigner. But his role quickly shifted. He became the crucial liaison, the know-how transferer, between the theoretical physicists in Chicago and the massive DuPont Corporation. DuPont was building massive, industrial-scale nuclear reactors at the desolate Hanford site in Washington state to produce the plutonium Wheeler's math had predicted. The friction was immense. Physicists wanted to run experiments and take risks. DuPont engineers demanded strict industrial safety margins, frozen blueprints, and massive cooling mechanisms. Stuck in the middle, Wheeler moved his family to Wilmington, Delaware, to work with DuPont executives and eventually out to the isolated frontier of Richland, Washington. His official job was to anticipate unknown problems, to look under the bed for monsters. In September of 1944, a massive monster reared its head. The B reactor at Hanford, the first large-scale plutonium production reactor in human history, was completed. They slowly withdrew the control rods, the power level steadily rose, and the chain reaction sustained itself. Enrico Fermi and DuPont executives were there for a moment of absolute triumph. But a few hours later, the reactivity slowly but steadily dropped. Even after pulling the control rods completely out, the power levels plummeted until the reactor went totally dead. With the entire pressure of the United States military breathing down their necks, they initially feared a mechanical blockage or structural flaw. But Wheeler noticed a peculiar pattern. After being dead for several hours, the reactor miraculously started to come back to life on its own. He deduced that an atomic byproduct of fission was poisoning the reactor. Using the concept of a nuclear cross-section, the effective target area a nucleus presents to a flying neutron, Wheeler realized that an isotope called xenon-135, produced indirectly by fission, had a massive cross-section. Millions of times larger than most elements, it was like a giant gaping crater, acting as an incredibly efficient neutron sponge, absorbing free neutrons and starving the chain reaction. Because xenon-135 is unstable with a half-life of about 9 hours, it decayed away while the reactor was dead, allowing the chain reaction to restart. How did they fix a machine inherently designed to poison itself? Wheeler's earlier friction with DuPont saved the day. During design, engineers wanted a precise number of fuel tubes, but Wheeler, ever cautious, aggressively fought to include hundreds of extra empty tubes in the corners. Building in a massive margin of error to look under the bed for monsters, he ensured they simply loaded extra uranium into those unused tubes. They overpowered the xenon sponge, kept the chain reaction going, and single-handedly saved the Manhattan Project's schedule. But the profound emotional core of Wheeler's story is that while he was solving the most high-stakes physics mysteries on the planet, he carried an unbearable personal burden. His younger brother, Joe, was in the infantry fighting through the grueling Italian campaign in Europe. Joe knew his older brother was working on a secret project that could potentially end the war. In the summer of 1944, Joe sent John a postcard from the Italian front. It had only 2 words written on it: "Hurry up." It was a desperate plea for survival. Wheeler worked 18 hours a day, pushing himself to the brink of exhaustion. But tragedy operates on its own timeline. In October 1944, just a month after Wheeler solved the reactor crisis, but 9 months before the bomb was tested, Joe was killed in action in Italy. Wheeler's devastation was absolute. compounded by a crushing, permanent sense of personal guilt. He stated, "I couldn't stop thinking then and haven't stopped thinking since that the war could have been over in October 1944. He believed that if he had driven to Washington, D.C. back in 1939 and demanded a crash program, the bomb would have been ready a year earlier. Joe and millions of others would have survived. He harbored a desperate, agonizing wish that he could somehow reach back in time to alter the events of the past. Is it any wonder that a man consumed by that specific grief eventually devoted his life to quantum theories that suggest the present observer can retroactively alter the past? On a subconscious level, it is as if he spent the rest of his life searching the cosmos for the mathematical mechanism that might have allowed him to answer his brother's postcard in time. He could not fix 1944, so he tried to decipher the fundamental nature of time itself. Logically, you might think that after experiencing the devastation of Hiroshima and Nagasaki and suffering the horrific loss of his own brother to the machinery of war, a scientist might step away from weapons of mass destruction. Many of his Manhattan Project colleagues did exactly that. They became staunch pacifists and advocated for international arms control. But Wheeler went in the exact opposite direction. The immense grief over Joe did not make him back away. It hardened his resolve. He believed weakness invited aggression. So when the Cold War began, that trauma drove him to push for the creation of something vastly more terrifying than the atomic bomb. This moves us into a tense paranoid era spanning 1949 to 1953. In August of 1949, the Soviet Union successfully tests its first atomic bomb, codenamed Joe 1. The American monopoly on nuclear weapons is instantly shattered. The psychological shock to the United States was profound. The government and the public were swept up in absolute paranoia. Air raid drills became a standard part of elementary school education, and the specter of a sudden nuclear apocalypse was suddenly a very real everyday anxiety. Within the tight-knit community of elite nuclear physicists, a massive, bitter debate erupts. Do we escalate? Do we build the hydrogen bomb? The super bomb? To understand the stakes of this debate, we must understand the physics. The bombs dropped on Japan, the ones Wheeler helped build, were fission bombs. They split heavy atoms. A hydrogen bomb, or a thermonuclear weapon, relies on nuclear fusion. It forces light atoms, like hydrogen isotopes, to fuse together into heavier elements, releasing energy in the exact same process that powers the sun. But fusion is immensely harder to achieve than fission. Because atoms have positively charged nuclei, they desperately want to repel each other. To force them to fuse, you have to overcome a massive Coulomb barrier. The only way to do that is to generate temperatures and pressures so extreme that they only exist in the center of stars. How do you do that on Earth? The spark plug required to ignite a hydrogen bomb is literally a fission atomic bomb. You use a nuclear explosion just to generate the heat needed to start the fusion explosion. The resulting blast is thousands of times more powerful than a fission bomb. It is a weapon of civilization-ending capability. J. Robert Oppenheimer, the man who had famously directed the Los Alamos laboratory during the Manhattan Project, strongly opposed a crash program to build the H-bomb. He argued against it on technical grounds, but primarily on moral grounds, viewing it as a weapon of genocide that served no tactical military purpose. Wheeler violently disagreed with Oppenheimer. We must examine Wheeler's mindset here objectively. He was not a warmonger who just enjoyed the intellectual thrill of designing bigger explosions. He operated from a deeply ingrained belief that extreme weapons were paradoxically extreme lifesavers. He viewed it entirely through the lens of deterrence. His trauma over Joe made him view overwhelming, unassailable military superiority as the only mathematical way to prevent a third world war. He famously stated that the most important peacetime use of nuclear energy was preserving the peace. If the Soviets were going to build a superbomb, the US had to have it first to hold them in check. Driven by that conviction, Wheeler teamed up with Edward Teller, the physicist widely known as the father of the H-bomb. They aggressively lobbied the government and the military to bypass Oppenheimer's objections and build the super. When President Truman greenlit the project, Wheeler went all in. He set up a highly classified research group at Princeton called Project Matterhorn to tackle the incredibly complex, mind-numbing calculations needed to model thermonuclear fusion. At the exact same time, he was directing the conceptual design group out at Los Alamos. He was running two massive, highly classified projects on opposite sides of the country. The amount of stress he was under is hard to comprehend. These scientists genuinely believed that the fate of the free world, the survival of Western civilization, rested directly on whether they could solve these equations faster than the Russians. Exhausted, pushing his mind and body to the absolute breaking point, constantly traveling and carrying the weight of the world's most destructive secrets, Wheeler stumbled into one of the most absurd, almost darkly comedic moments in the entire history of nuclear espionage. It is January 1953. Wheeler had just finished reading a highly classified, 6-page document that outlined the history, the progress, and the deep technical secrets of the hydrogen bomb program. This piece of paper was quite literally the most sensitive, dangerous document on the planet at that exact moment. He placed it inside a white envelope, and then placed that envelope inside a larger manila envelope for transport. He boards an overnight Pullman sleeper train, traveling from Philadelphia down to Washington, D.C., with the ultimate secret of the Cold War in his suitcase. Late at night, in his private sleeper berth, Wheeler takes the envelope out to review it before his meetings. After reading, he decides he needs to use the train's washroom before going to sleep. In an abundance of caution, or perhaps a lapse of judgment, driven by sheer exhaustion, he decides he cannot leave the document alone in his berth. So he takes the manila envelope containing the nuclear codes with him into the train's lavatory. Once inside, he sets the manila envelope down on the washstand, or possibly behind the pipes of the sink. He uses the facilities, washes his hands, walks out of the lavatory, heads back to his berth, and in a moment of sheer absent-mindedness, leaves the blueprint for the apocalypse sitting in the bathroom. The sheer absurdity of the human condition in one moment. Wheeler realized his mistake relatively quickly, perhaps within minutes, and rushed frantically back to the lavatory. The outer manila envelope was still there on the washstand. But when he looked inside, the inner white envelope containing the 6 pages of thermonuclear secrets was gone. A massive, desperate FBI investigation followed. They ripped the train car apart and interviewed every passenger, escalating the crisis all the way up to the newly inaugurated President Dwight D. Eisenhower. They were terrified a Soviet spy had been trailing Wheeler and snatched the document. To this day, the fate of that document remains an unsolved mystery. The most likely mundane explanation is that the train porter came in right after Wheeler left, saw a plain white envelope, swept it up with the trash and tossed it, but they never found a shred of it. Wheeler received a severe official reprimand from the Atomic Energy Commission, a humiliating incident that almost entirely ended his career in government science. Even the geniuses building the machinery of the apocalypse are still just sleep-deprived guys who leave things in bathrooms. But this incident seemed to break the fever for Wheeler. Following this era of intense geopolitical tension, he pivots incredibly hard. He abandons the physics of destruction, leaves weapons behind, and decides to resurrect the forgotten physics of the cosmos. He steps away from the military-industrial complex and transitions into what he called his second major phase. Everything is fields. Moving into the 1950s through the 1970s, he turns his attention back to Albert Einstein. In the 1950s, Einstein's masterpiece, The Theory of General Relativity, which describes gravity as the curving of spacetime, was actually considered a dead end, an academic backwater. The cutting edge of physics was all about quantum mechanics, discovering new subatomic particles and developing quantum electrodynamics. General relativity was viewed as beautiful, but ultimately practically useless, considered too intensely mathematical and completely detached from any testable laboratory experiments. But Wheeler decides this discarded theory is exactly where he wants to plant his flag. During this period, he became the ultimate scientific branding expert, an iconic literary editor for the universe. He had an incredible knack for taking deeply opaque math and giving it a name that captured the public's imagination. Before Wheeler got involved, astronomers mathematically theorizing about what happens when a massive star dies and collapses had a clunky, terrible name for it. A gravitationally, completely collapsed object. Precise, but devoid of imagination. In 1967, during a conference, Wheeler was searching for a better term and famously solidified the terminology while brainstorming in a warm bathtub. He coined the term black hole. It was an instant masterstroke of branding. The entire world, not just scientists, but sci-fi writers and kids looking at the stars, could visualize a hole in space so dark and dense that nothing can escape. He also popularized the term wormhole to describe a theoretical tunnel connecting two disparate points in spacetime, and he coined the phrase quantum foam to describe the jittery, violent, bubbling foundation of the universe at the absolute microscopic level where space and time itself break down into chaos. He wasn't just a marketer slapping cool names on other people's math. He was pushing the boundaries of Einstein's curved spacetime to absolute extremes that even Einstein was uncomfortable with. Wheeler became obsessed with an idea he called geometrodynamics. He wanted to know if you could explain everything in the universe using only the geometry of empty space. He was asking what happens when matter is completely crushed out of existence in a singularity, a point of infinite density. He explored the radical idea that perhaps at the fundamental level, particles of matter don't actually exist at all. He called it mass without mass. Wheeler theorized that what we perceive as a solid particle with mass, like an electron or a proton, might actually just be an incredibly tight, localized knot or twist in the invisible fabric of spacetime itself. From a distance, that trapped energy looks and acts like a solid particle, but zoomed in infinitely close, you would just find empty space bent into a topological knot. The fabric of reality itself is what creates the illusion of solid objects. While geometrodynamics didn't ultimately succeed as a theory of everything, his exploration of it birthed modern astrophysics. And perhaps his greatest legacy from this era wasn't just his own theories, but the minds he shaped. Wheeler was a legendary mentor. He was the doctoral advisor for a roster of students that reads like the Hall of Fame of modern physics. He mentored Richard Feynman, who went on to win the Nobel Prize for quantum electrodynamics. Kip Thorne, who won the Nobel for the first direct detection of gravitational waves, and he advised Hugh Everett, the man who invented the many worlds interpretation of quantum mechanics, the concept that every quantum choice splinters reality into parallel universes. Wheeler was basically the editor who took the raw, chaotic genius of these young students and molded it into Nobel-worthy shape. His mentoring style was a study in contradictions. On the surface, he was unfailingly polite, soft-spoken, and maintained an air of old-school academic formality, always wearing a formal suit and tie. But underneath, he was fiercely strict and demanded absolute conceptual clarity. He wouldn't let his students hide behind walls of complex equations if they didn't intuitively understand the physics. When the brash, Brilliant Richard Feynman skipped over a few intermediary mathematical steps at the chalkboard to get to the conclusion faster. Wheeler stopped him cold. He said, "Little steps for little people." From Wheeler, it wasn't an insult. It was a demand for rigor. His point was that if you can't explain every single microscopic step of the transition, you don't actually understand the mechanics of what you are describing. But he wasn't a total stuffed shirt. He had this bizarre, mischievous streak. In 1971, a formal, highly prestigious banquet was held in his honor at the Carlsberg Mansion in Denmark for his 60th birthday. The room is filled with Nobel laureates and dignitaries in tuxedos. Wheeler, sitting at the head of the table, looking perfectly distinguished and calm, secretly pulls out a string of firecrackers, lights the fuse, and drops them directly behind his own chair. The firecrackers go off in a massive series of bangs, causing absolute chaos and panic among the diners jumping out of their seats. And Wheeler just sits there, completely unmoving, sipping his drink with a completely straight face, pretending he has absolutely no idea what is happening. He never lost that mischievous spark of the 10-year-old boy who loved Dynamite, that desire to disrupt the quiet room, just to see what happens. So we have a man who has spent decades studying the heaviest, most massive objects in the universe. He has mapped the crushing weight of black holes. He has built atomic bombs. But as he aged, entering the final decades of his life, this man of deep, heavy physics came to a shocking conclusion. He decided that mass, matter, and even the fields of space-time he had championed might just be an illusion. This is where we cross the threshold into his third, final, and undoubtedly most profound intellectual phase. We are moving from everything is fields to everything is information, spanning the 1980s right up until his death in 2008. Wheeler published a paper in 1989 that introduced a catchphrase that shook the foundations of modern physics. He called it from bit. Drawing inspiration from the rise of computer science and information theory, pioneered by people like Claude Shannon, Wheeler proposed that the universe is, fundamentally, at its deepest bedrock level, binary. It is made entirely of yes-no choices. He argued that every particle of matter, every photon of light, every field of force, even the fabric of space-time itself, derives its very existence entirely from the apparatus elicited in answers to yes or no questions, or bits of information. He wasn't suggesting there is a literal silicon computer sitting outside the universe running a program, like we live in some simulation. He was proposing that the universe is an information processing system. Physical matter and energy aren't the fundamental building blocks of reality. Information is. Matter is just the physical manifestation of that underlying information. A photon isn't a thing. It's a bit of information about the universe's state. This radical shift in perspective leads directly to his most controversial and frankly most difficult idea, the participatory anthropic principle, often referred to as the PAP. To illustrate this, he drew a very famous, very strange diagram. A giant letter U. Picture a large, thick letter U. At the very top of the right-hand branch, the universe begins with the Big Bang. As you move down the right side and around the curve at the bottom, time passes. The universe grows, expands, stars form, and galaxies collide as billions of years pass. Eventually, as you move up the left-hand branch of the U, biological life emerges and consciousness evolves. And what's at the very top of the left branch, completing the shape? A giant eyeball, an observer. That eyeball is looking all the way back across the empty space between the branches, staring directly at the Big Bang on the right side. The metaphor here is staggering. The universe goes through billions of years of evolution, specifically to create observers. And those conscious observers look back at the universe, and the very act of their observation, the act of asking questions about the universe, is what gives tangible, solid reality to the universe, even all the way back to its origins. Now, this might sound dangerously close to New Age mysticism. Is he seriously suggesting that human consciousness magically creates matter? Wheeler himself was hyper-aware of how his ideas could be hijacked by mystics and charlatans, and he violently hated pseudoscience. In 1979, he actively petitioned the American Association for the Advancement of Science to kick the field of parapsychology out of the organization. He famously handed out a pamphlet at their convention with the slogan, "Where there's smoke, there's smoke." Meaning, if something looks like a hazy, undefined illusion, it's just an illusion. There is no actual fire hidden behind it. Wheeler wasn't saying that human wishes, intentions, or vibes change physical reality. His theories were grounded strictly in quantum mathematics and testable laboratory experiments. He was saying that the physical act of measurement, the interaction between a quantum system and a macroscopic measuring device, forces quantum probabilities to collapse into definite facts. To explain this without complex equations, let us use Wheeler's own brilliant analogy, a modified game he called -20 questions. In normal 20 questions, a word exists in someone's head from the very beginning. But in Wheeler's negative version, imagine you are sent out of the room, and the rest of the people agree not to agree on a word. There is no predetermined word. The only rule is that when you come back in and ask a question, the person answering must give a truthful yes or no that is logically consistent with all the previous answers given. You walk back into the room. You ask the first person, "Is it an animal?" The first person thinks of any random animal, let's say a dog, and answers yes. The word dog isn't the agreed-upon word, but a parameter of reality has now been established. It must be an animal. The next person you ask, "Is it bigger than a bread box?" has to think of an animal bigger than a bread box, like a horse, to keep the game logically consistent, and answers yes. As you ask more and more questions, the universe of possible answers rapidly narrows down, getting tighter and tighter. Finally, on the 20th question you ask, "Is it a kangaroo?" The last person, forced by the logical chain of all the previous 19 answers, realizes a kangaroo fits perfectly and is forced to say yes. The word kangaroo did not exist in the room until the specific sequence of questions you asked forced it into existence. Your questions built the reality. Wheeler argued that this is exactly how quantum mechanics operates. Before you measure a subatomic particle, it doesn't exist in a definite place or spinning in a definite direction. It exists in a fuzzy, undefined cloud of mathematical probability, a superposition of all possible states. Wheeler poetically called this undefined state a smoky dragon. We can see the dragon's tail where the particle was emitted, and we see its biting mouth where it hits our detector. But the body in between is just smoke. Only when you force the universe to answer a yes or no question, by setting up a physical detector asking, "Are you here or are you there?" does the particle collapse out of the smoke into a definite physical reality. The act of setting up the experiment and asking the question creates the answer. To prove this wasn't just dorm room philosophy, Wheeler devised one of the most brilliant thought experiments in history. In 1978, called the delayed choice experiment. Incredibly, technology advanced enough that it was actually successfully performed in a laboratory in 1984. We must quickly revisit the classic double-slit experiment. If you shoot a single photon of light at a barrier with 2 slits in it, and you don't track its path, it acts like a wave, passes through both slits simultaneously, and creates an interference pattern on the wall behind it. But if you put a detector right at the slits to see which specific slit the photon goes through, it acts like a solid particle, goes through only one slit, and the interference pattern disappears. Wheeler took it a massive step further. He said, "Let's delay the choice of whether to measure it or not. Let the photon pass the barrier with the two slits. Let it travel further down the optical bench. While it is in mid-flight, after it has supposedly already crossed the point where it had to decide whether to go through as a wave or a particle, the experimenter uses a high-speed switch to randomly choose whether to turn the final detector on or off. The laboratory results are staggering, and they completely validate Wheeler. The choice you make at the very last microsecond, at the end of the path, determines how the photon behaved in the past at the slits. If you choose to measure its specific path at the very end, it turns out it traveled as a single particle through one slit the entire time. If you choose not to measure its path, it turns out it traveled as a wave through both slits the entire time. The present decision retroactively determines the past history of the particle. The effect precedes the cause. The past does not exist in a definite state until it is recorded in the present. Wheeler, being Wheeler, scaled this up to the absolute cosmic limit. He proposed a version of this experiment using the entire universe as the laboratory. Imagine a quasar, an unimaginably bright, active galaxy sitting billions of light years away from Earth. Between us and that quasar, sitting exactly in the middle, is another massive galaxy. The immense gravity of that middle galaxy acts like a magnifying glass, bending the light of the quasar around it in what is called a gravitational lens. It splits the light from the quasar into two distinct paths. One path goes around the left side of the galaxy. The other path goes around the right side. That light has been traveling for billions of years, starting its journey long before the Earth, or our sun, even existed. Tonight, an astronomer walks into an observatory and points a telescope at that light. According to Wheeler's mathematically validated delayed choice theory, the astronomer's decision on how to configure the telescope tonight determines whether that photon took the left path, the right path, or took both paths simultaneously billions of years ago. The implications are almost too massive to hold in your head. Consciousness is not just some cosmic accident that happened to evolve on a wet rock in a random solar system. Consciousness is the fundamental, necessary mechanism required to finalize the universe. It is an incredibly profound philosophical shift, perhaps the biggest since Copernicus. Without observers to process information, to set up detectors and ask questions, the universe remains in a state of indefinite fuzzy potential, an unfinished script, a smoky dragon. We are not just passive spectators sitting in the audience of the cosmos. We are, as Wheeler put it, the co-authors of reality. And looking at the entire arc of his life, that brings us full circle to that devastating tragedy of his brother Joe during World War II. Wheeler couldn't change the past in 1944. He couldn't go back and speed up his own research to save Joe from that battlefield in Italy. The guilt of that fixed timeline haunted him forever. But he spent the rest of his life proving, mathematically, that the past is not actually a fixed, immutable thing. He proved that in some deep, fundamental quantum sense, the present observer does shape history. It is a beautiful, melancholic, and tragic testament to how deeply human our pursuit of hard science really is. We like to think of physics as cold and objective, but our greatest theories, our most profound models of the universe, are often born directly from our deepest personal wounds and our most desperate desires. Wheeler was trying to fix time, so after this massive journey through explosions, grief, black holes, and the deconstruction of reality, what does this all mean for you listening? Think about the sheer magnitude of what Wheeler proved. Tonight, when you step outside and look at a distant star, the photons hitting your retina have been traveling through the freezing, silent void of space for millions, maybe billions of years. And for all that time, they existed in a state of fuzzy probability, a quantum haze. A smoky dragon stretching across the cosmos. But in the exact fraction of a second that you look up, in the moment your conscious mind registers that light, you force that photon to collapse out of the probability cloud. You force it to have a definite, singular history. You are reaching back across eons of time, across the unimaginable, terrifying depths of space, and you are cementing the past simply by witnessing the present. You aren't just observing the universe is using you to bring itself into existence, and that is the lasting legacy of John Archibald Wheeler, a man who blew off his own fingers as a curious boy, who helped build the horrific weapons that defined an age of global terror, who named the black holes that consumed dead stars, and who ultimately left us with the awe-inspiring realization that we are essential to the fabric of reality itself. We are the universe figuring itself out. If this exploration of reality and history expanded your mind, make sure to like this video, share it with a fellow curious thinker, and subscribe to Legendary Lives Unveiled for more incredible stories. Leave a comment down below to solidify our shared reality, because your interaction doesn't just help the channel. If John Wheeler was right, your observation is literally keeping us in existence. Thanks for listening.